Hello everyone, I'm a senior data scientist at SAP in the Internet of Things area, and within this area I'm particularly involved in the development of a product called Vehicle Insights, which is a cloud offering designed to collect telemetry data from vehicles and gaining business insights from this type of data. So working with telemetry data as a data scientist, I realized that this comes with some caveats, and I thought it might be worthwhile to share them with you. But before I start off telling you about all the grand possibilities of what you can do with sensor data, I would like to encourage you to imagine the opportunities yourself. And I have collected a few screenshots on the type of services that I imagined you would come up when thinking about these questions. For example, when you shop online or with a loyalty card, you provide information about which other products you might like, and of course they're trying to sell you exactly these products. Or your email program might automatically prioritize your email inbox based on your prior feedback, or also based on your behavior. For example, if you look at an email for a longer time, or you open it in a separate window, that indicates that this email is probably of a higher priority for you. But many data-driven services are not generated by data that you have provided yourself, but by data that was generated by a sensor in your environment. For instance, your mobile phone signal is tracked together with millions of others, and it is aggregated in order to provide a more accurate prediction of road traffic jams. Or in most big cities, trams or buses are equipped with telemetry devices that make it possible to predict when the next tram will arrive at your station. So the human-generated data was around in the internet for a while, but the amount and the quality of the sensor data that becomes available and that is generated by lifeless things that are just connected to the internet is increasing more and more at the moment. And with the number of connected devices, new opportunities to take advantage of this data pops up everywhere in so many different business areas, really, from smart cities to high-tech farming, connected manufacturing. However, the examples that I will present here will mainly be coming from the area of connected vehicles, because this is the field that I'm working in at SAP, and these are the examples that I best know about. But I think you should be able to apply these insights also to other business fields where sensor data plays a role. This is the agenda of the remaining webinar. At first, I will show you some examples of how analytics of dense sensor data is applied to different businesses and how it creates value. And as I mentioned, this will be mainly in the field of connected vehicles. I will then touch on an experience that I made myself when working with different customers, namely that in most applications it's not so much of interest to just get a good prediction or get some single key figure right. Instead, you often want to gain a deeper understanding of the relationships within the data. And one powerful tool to achieve this is a method called regression analysis, which I will just introduce briefly. And I will then close with a few pitfalls that you have to watch out for when you're working with sensor data. Okay, so when looking into the industry examples, the case of digital farming is probably a surprise to some of the listeners, but in fact modern land machines like tractors or combines are fairly high-tech. these land machines conduct chemical analysis of the soil, and they can also capture what is being done on a certain area of a field. For example, the amount of fertilizer that has been brought out. This data can be combined with other data, for example, weather data, or with biomass data that we can get from satellite images to help the farmer to make a better decision. For example, when to harvest, or which fertilizer or which pesticide to use, and how much pesticides to use and when to apply it. These decisions are really crucial. If you, for example, bring out the wrong fertilizer at the wrong time, it can really have a huge impact on the quality of your product. A second field where sensor analytics plays a big role and is really popular is in the analysis of road traffic. This is a service where many different stakeholders are actually interested in. So, for example, municipalities or public services, of course, would like to reduce traffic problems and also pollution problems. And by analyzing the data, they can find out how different traffic impediments like roadworks, but also things like traffic lights or bus stations, can impact the traffic flow, and they can optimize the planning of their city according to that. They also analyze individual travel patterns so that they know common journeys that are being made through the city and can then offer alternative mobility services. The individual drivers, of course, are interested in avoiding traffic jams and having a more precise estimate of the travel time. But there are also businesses that can take advantage of that data. So maybe a short personal anecdote. When I was talking to a large industrial customer, I learned about the job of a gate manager, something I've never heard before. So imagine a big manufacturing site with lots of trucks delivering or picking up goods over the course of one day. Since it's a manufacturing site, the internal processes of the plant are very rigidly organized by a very precise and tight schedule. However, a scheduled truck might arrive 2 hours early or 2 hours late. If the truck's coming from very far away, it might arrive 2 days late. It's really, I've been told that's really nothing unusual. And at the truck gate, the sort of the rigid world of the internal manufacturing processes meets the unpredictable world outside. So having better information about when the trucks actually arrive helps the gate manager to organize the loading of goods in a more efficient way. Another field where it's quite popular to analyze sensor data is in the field of remote vehicle diagnostics. So connecting devices to the internet is also a very big trend in the automotive industry. So not only a single car, but also more and more parts of a car are connected to the cloud. And these parts provide important information about the vehicle health. This telemetry data can then be used, for example, to diagnose a problem remotely before the car even enters the repair shop. Sometimes even before the driver might realize that there's something wrong with his vehicle. So, of course, SAP is involved in many other areas that involves analyzing sensor data, but this is just a small excerpt from the fields that I know about best. In this webinar, I would like to delve a little bit more into the data science side of this. And by doing this, I also build on some topics that my colleague Paul Pallett has covered in a previous webinar. So what Paul presented in this introductory webinar was also a schematic description of the predictive modeling process. So the kind of process that you use in order to solve most data science problems. So in data science, you usually work with statistics. So you have a population of different objects that are described by different attributes. In this example, it's a collection of dots that have different colors, red and blue, and they have different shapes like circles and stars. But imagine each of these dots has many other attributes that describes one dot and that you can't see in this picture, but that are there. Of course, when you do data science, you usually don't have all the information at hand. You usually work on a subset of the whole population. So you have to make a sample. And the aim of the whole process is to get to a prediction function. This prediction function can predict different aspects of an object. So in our case, it could be a function that predicts the shape of an object, or that predicts the color, or both. And it performs that prediction based on all attributes that are available for one object, except, of course, for the target attribute that needs to be predicted. So let's say we have one object where we know the color and we know other things of that object. Then the top prediction function would then estimate what is likely to be the shape of the object. And the way to get to such a prediction function is usually a iterative process where you train a statistical model by presenting it some example objects, and then you test your model by presenting them other example objects that you haven't used for training the model. And from that test you get to compute some error metrics, and you can use these metrics again to improve your prediction function. I think Paul also explained in his webinar that there are many different types of sort of problem classes that can be solved by data science, and that are often applied to business problems. I will not go through all of these classes, just the first two, in order to give you a flavor. So in the first case, in the regression case, we present the computer with a set of objects, and we let it learn a specific quantity that is related to these objects. For instance, your set of objects could be customer invoices, together with the amount of time it took the customer to pay. And the amount of time it takes the customer to pay would be the target value. With a regression, you can use historical data to learn the relationship between the invoice attributes and the time it takes the customer to pay. And this model can then be used to predict the delay in payment for new invoices that you haven't seen before. Classification is a very similar thing. The difference is that the target value is not a quantity, but it is a class. In this picture, you see that the different classes are the red and the green dots, and you want to find a function that helps you predicting for a dot if it's a red or a green one. This is exactly the same as the example that I presented you before with the blue and the red dots that sometimes are circle-shaped or star-shaped. The difference to regression is that the target value is a discrete value rather than a continuous one. The important thing to take away from this slide is that there are different classes of learning problems, and I want to introduce you to just another type of learning problem that when you solve it, it can help you gain insight into the data that goes a little bit beyond mere prediction. And this method is called regression analysis. So a regression analysis is something different than regression. In regression analysis, it's all about capturing the relationship between variables, specifically with a focus on the relationship between a dependent variable and multiple independent variables. Now this is of course very abstract, and I try to make it a little bit more concrete. The predictor variables might be the attributes of the object that we inspect. For example, the customer invoice, the customer, the area the customer lives in, the purchases the customer makes, and the dependent variable would be the delay in payment. So the difference to mere regression is that we are not so much interested in the actual estimate, but we're more interested in the factors, the independent variables, and how they influence the target variable. So in our invoice example, the customer might be predicted to pay very late because he or she purchased electronics, and electronics customers tend to have a bad payment morale. And we're more interested in the relationship purchased electronics, hence negative impact on payment morale. We're not so much interested in how many days the customer actually exactly takes to pay the invoice. I still think probably this is still a little bit abstract for you, and in order to make this concept yes a little bit more tangible, I'd like to show you some examples from my work where we use this approach. So as it is a little bit dangerous to show you cases that come from actual SAP customers in a public webinar, they might object to that. I will instead show you some prototypes that we created in the lab. So these things are not part of any SAP product. Don't expect them to be in the price list tomorrow. The first example that I want to present is an example about fuel efficiency. So, of course, many owners of a car or many fleet owners would like to reduce their fuel consumption, as fuel is costly, and it's also very bad for the environment if you consume too much fuel. And some of them might already know that they consume maybe more fuel than they should. However, they don't know why they consume so much fuel, because fuel consumption is influenced by many different factors. It's influenced, of course, obviously by your driving behavior. So if you drive at very high speeds, or you drive in a very hectic way, you tend to use more fuel. But fuel efficiency is also very much influenced by the weather, by the road conditions, by the traffic, etc., etc. And you can use regression analysis to separate all these factors and really pin down for a certain driver which factors contributed in which way to his fuel consumption. So the outcome was a prototype UI like that. So this is a personal fuel efficiency report for one driver that was equipped with whose car was equipped with a telemetry device that captures the GPS location on a regular basis, and also some information from the engine. And we combined this data set with geospatial data and came out with the following regression analysis. So what you can see here on the page is that I ask you to focus specifically on the table on the top left. This really displays all the condensed information. You can see for the driver the fuel consumption per 100 kilometers, but also per month. And the driver can also see how he or she ranks within the fleet. But the driver can also see the different factors that contributed to the fuel consumption. So, for example, you see the behavior score that contains factors like whether the driver accelerates or brakes suddenly, or whether the driver drives in a very low gear if it's a manual gear car. But there are also other factors like the traffic score or the route score. The route score contains factors like the incline of the road or the curvature of the road and similar things. So in our example, the driver can be actually very happy because the driver saves a lot of fuel by showing a very smooth driving behavior. However, the driver could improve and save another liter of fuel per month if he or she would avoid to travel at peak times, as the traffic score is not so favorable. Another thing that we can do with this telemetry data is, of course, also to gather statistics about the traffic flow on some of the roads that are often traveled. What you can see here an example of a map with some of the roads being color-coded. So these were the roads where we had enough data to actually gather statistics and display, if the traffic flow is smooth or if the traffic flow is a little bit slower than expected. This is, I think, a snapshot from a Monday 8:30, sort of the rush hour commuting travel time. And what you could do with that data first is you can attempt to do a regression. So you predict the speed of the traffic flow depending mainly on the road, the weekday, and the time of the day, based on data that you have collected from the past. But what you could also do, and what's much more exciting from an insight point of view, is you can also enrich the data with other data sources, particularly with information about roadworks and with road information from a geocoding service like OpenStreetMap. And you can try to figure out how different traffic impediments impact the traffic flow. The first project that I showed you was successful. We were able to find the factors that influence fuel economy. The second one was not so successful, and I will show you later on during the webinar why we didn't succeed. So this was just to give you a brief idea of what regression analysis is good for. And now I would like to give you a small flavor of how you can approach regression analysis. So the simplest and most common approach is called linear regression. Linear regression is basically finding a linear equation that fits the data best, and the coefficients from this equation are then used to explain the relationship between the variables. So the example chart here is coming from a set of cars with different attributes like the weight or the power of the engine. And what you can see in the plot is a two-dimensional chart that plots where every dot on the chart represents a type of car, and it plots the fuel efficiency within the city traffic against the engine power. And as you can see with the line that's going through the dots, is that with increasing horsepower of the car, the fuel efficiency deteriorates. But of course, this approach also works when you have more than one attribute. So If you have more than one attribute, you can't make a nice chart out of it, but you can consider many more factors. But the output of such a linear regression will not then be such a nice plot, but what you get is a tabular output. On the right side of this slide, you can see a typical output from a linear regression model, and from this output the trained eye can read, for example, that the fuel economy is slightly negatively impacted by the engine side, by the engine size, engine power, and it's even more strongly negatively impacted by the weight of the vehicle. Okay, so linear regression is a very good approach that works very reliably and is very robust in many cases. However, it has a few drawbacks, and the main drawback is that if the relationships between the variables are not linear, the approach is not directly applicable. So what you have to do if the relationships between the variables are non-linear, but you want to use linear regression, is you have to transform all the attributes in such a way that the regression problem becomes a linear regression problem. And that can be very hard work that involves a lot of data analysis and can keep your data scientists busy for quite some while. So if you have a problem that is a little bit more complex, what you want to do is maybe looking for more generic approaches. And there are other regression analysis approaches than linear regression that also work fairly well out of the box and that are applicable to a wider range of problems. For example, SAP has its own regression algorithm that is called SAP auto regression. And that works pretty much out of the box without much configuration or tweaking required. And it's also famous for being extremely robust to sampling errors, for instance. But to be fair, I should also mention that there are other regression approaches that are public domain and that also work fairly well out of the box, the most famous one being a method called gradient boosting. And what such regression algorithms can do is shown in this example chart. Again, I'm taking a two-dimensional example, but you can apply these approaches to learning problems where your objects have many, like hundreds of attributes. So this is also applicable to multidimensional problems. But in order to visualize it, I chose a two-dimensional plot. So this is an example from the vehicle data that I explained before. You remember I presented you some examples for regression analysis that we made in the lab, and one of these examples were concerned about traffic flow. And this chart is from this traffic flow example. Each point that you see on this plot represents a vehicle that travels on a certain heavily traveled road that goes towards SAP's headquarters in Germany. And we plot vehicle speed against the time of the day. So at the chart you can see that we took only we didn't plot the whole day, but we only plotted the time between 7 a.m. and 10 a.m., which should contain the main commuting peak times. And if you would just see the points on the diagram and not the regression line, the diagram would be pretty unintelligible. But with the regression line, you can see that the traffic tends to flow much slower between 8 and 9 a.m., which should be no surprise because this is the main sort of peak travel time for commuters to SAP. And when you draw a horizontal average line through the chart, you can also infer how the time of the day impacts the traffic flow, and by comparing these two lines, you can figure out how the time impacts the travel speed on that road. So these generic approaches are fairly powerful, and I would recommend you to use them as they're very easy to apply. They're applicable to many sorts of problems, also nonlinear ones. As I mentioned before, they're not only applicable to two-dimensional problems, but to problems with many, many predictors. They usually have some way to take a set of many, many predictors, and out of that set they select those predictors that have a statistically significant influence on the target value, and they discard the other ones. Of course, this all sounds a little bit too good to be true. Why would anyone use linear regression when you have these out-of-the-box algorithms? You have to say that you also pay a price for the convenience that you get from these automated algorithms. So you pay a little bit in either robustness or accuracy. So auto regression tends to be very robust but a little bit less accurate, and gradient boosting tends to be fairly accurate but not very robust. And if you pay the data scientist and take the effort to adapt a linear regression model to the data, you have spent a lot more money, but you also normally achieved a regression model that is much more accurate. So these are the trade-offs that you normally have to take. Okay, so these are the common approaches that at least I normally take to regression analysis, and I think most people in the data science community would do that as well. But no matter which approach you use, there are some pitfalls that you should look out for. These pitfalls also have names. They're fairly well known in the statistics community, and they're mainly there are confounding variables, they're hidden variables, and it's sampling bias. I will go through all of these three phenomena and explain them one after another. So confounding variables is when you have two influence factors that influence your target variable in a similar way, and if that happens, it's very hard to tell which of the influence factor was actually the one that causes your target value to increase or to decrease. So in our fuel efficiency example, we have the case that when the weather is bad, when it's rainy, you tend to use more fuel per 100 kilometers. But also, when you drive with a high engine speed, you also tend to use more fuel per 100 kilometers. The problem now is that in our data set, or generally in reality, these two things often co-occur. So when it's rainy weather, people tend to drive more cautiously, which means they drive in a lower gear, hence they drive with a higher engine speed. In such a case, it is impossible to tell whether your fuel efficiency deteriorated because of the rain or because of the engine speed. You really can't tell. A similar case is what you have with hidden variables. Hidden variables are actually worse because they're even more deceiving. Let's say we analyzed the telemetry data in order to make a regression analysis on the fuel efficiency, but we didn't take the road conditions into account. We only took parameters from the engine into account. Then we of course would have established the relationship that with a higher engine speed you consume more fuel. However, what we failed to see is that whenever you drive up a hill, so when the road inclines heavily, then you have to drive with a lower gear, hence you drive with a higher engine speed. So we failed to see the actual cause of our fuel efficiency being bad because we didn't consider the fact that the incline of the road might have an impact on the fuel efficiency. And yet another hazard that you have with regression analysis is something that we call sampling bias. And sampling bias was actually the reason why in our lab experiment we failed to establish the relationship between road impediments and the traffic flow. You remember I introduced you to the example where we had statistics about the traffic flow and we had some auxiliary data about traffic impediments, and we wanted to see how the traffic impediments impact the traffic flow. Now, when you look at this road that is in the lower left corner of this map, that is fairly orange and red, so traffic flow is bad in this example. This is a road that, again, is a heavily traveled road that leads to the SAP headquarters, and on this road there are often traffic jams in the morning. So what we wanted to do was to figure out if the traffic delays that you have on this road, how much they are dependent on the time of the day. And we sort of assumed that during peak travel times you tend to have more traffic jams than during off-peak hours. However, we couldn't answer even that simple question because we had a sampling bias within the data that we looked at. The data set that we analyzed was a set of about 20 cars that drove around Germany, and all of the drivers of these cars were SAP employees that were working at the headquarters office. All of these employees, of course, being good employees, went to office in the morning and traveled this road at no other time of the day, which means the only telemetry data that we had was between 7 a.m. and 9:30 a.m. And with this limited time window, we really couldn't know if the traffic is better or just the same during other time. We simply didn't have that data at hand. So they're not only the general pitfalls that you get with regression modeling and that probably can be foreseen by any reasonably experienced data scientist that has a statistics background. But I also noticed that there are some challenges that are specific to sensor data and that you would not encounter, for example, with traditional sort of transactional data or other types of data. So firstly, the sensor values are often messy. The measurements of the sensors, of the different sensors, are usually not in sync. And lastly, the temporal component is often more important when you deal with sensor data than when you deal with other data, because you're basically looking at time series. So you often have to deal with changes that happen over time, but also with sudden changes that might invalidate your regression model. Okay, but I want to start with the messy sensor data. With respect to that, I would like to show you again an example from from my own work. This is again the data that we collected from the SAP employee cars, and this chart displays the engine fuel level of a car over the course of one 20-minute trip. And initially, for our fuel efficiency regression model, we wanted to use this parameter to determine how much fuel was consumed. And as you can see, the data is very messy, it's extremely noisy. Yet, with some fantasy, if you look at the data, half closing your eyes, you might you might guess that you probably used up 3 liters over the course of this trip, but it's still an incredibly noisy signal. But if it were only a noisy signal, we could have used smoothing techniques to get a good estimate of the real value of the real fuel consumption. But in the end, we could not use this time series, as the signal is not just noisy, but it's also unreliable. For instance, when the tank of the car is full, 100% full, the sensor would stick to the maximum value for a long time before it starts going down. So just the first sort of 20 minutes after you've filled up your tank to 100%, you would, according to this sensor, use 0 fuel per 100 kilometers. This again is also an issue that you could solve theoretically as a data scientist. For instance, you could filter out all the measurements that indicate 100% fuel level, but eventually found an easier way to estimate the fuel consumption, and I will show you in a later slide how we came to the real fuel consumption value. I also want to show you 2 other examples that I copied from the literature. First one is a raw data reading from a humidity sensor that has quite obvious outliers. This is a fairly easy case because this is a measurement failure that's very easy to detect, and it just happens from time to time, and you can filter out these errors quite easily. The second example is a little bit more difficult. What you see here is are 2 temperature sensors that measure the ambient temperature, and what you see in parallel is the battery voltage of the battery that serves the sensor with electricity. And as the battery runs out, the sensors start to fail to deliver the true temperature. And this failure would be much harder to handle. Firstly, it's very hard to detect because the transition into the failure mode is sort of smooth. You see, it doesn't immediately start measuring a temperature of 125 degrees centigrade, but it sort of slowly increases first until it increases to such absurdly high values that you can probably tell that the temperature is wrong. The second thing that makes this a very hard problem is also that once you have detected it, there's really nothing you can do to estimate the correct measurement value. Sensor measurements, coming to the next slide, sensor measurements are often also not in sync. And this can become an issue for you if you want to look at several sensor measurements at the same time. So picking up from the previous problem of estimating how much fuel a car uses at a certain moment, here's how we actually went about it and how we succeeded to estimate the real fuel consumption. The fuel consumption can be calculated from 3 different technical measurements that we got from the engine and that basically every car provides. If you want to combine these 3 measurements to calculate a 4th time series value, you need to bring these values in sync. And as you can see now with the dashed lines, for the mass airflow, we have the fewest measurements. So we take these time points as the sort of reference time points that we also use for the fuel consumption, for the calculated fuel consumption value. But the other values in the equation in the other time series don't quite match. So we have to interpolate. These values. This is, of course, a problem that you do not only have when dealing with vehicle data, but this is a problem that you have with any sort of sensor data, because all sensors essentially deliver time series data. And since SAP has started to invest more in software in the Internet of Things field, we're also in the course of developing tools that help you with these kind of data preparation steps. The third challenge that I want to point out to you is the fact that real systems often change over time, and as the reality changes over time, your regression model might fail to adapt to these changes. Some of these changes happen gradually over time, and you would constantly need to revalidate your model to see if it is still correct. And other changes happen discretely at a certain time, a time that we usually call a change point. And there are also some statistical methods that you can use to detect these change points. I would like to finish up with a Venn diagram that describes the kind of skills that you need in a data science team. So some people might claim you need all these skills in one person. I think that's maybe a little bit unrealistic, but you should have all these skills in a team. And the main circles that you can see are hacking skills, expertise in the subject matter, and statistics knowledge. So if you have all these 3 skills combined, you can do data science. And if one of the skills is lacking in your team, you're very likely to do something else than data science. And the most noticeable term that you can find here is the combination of only having subject matter expertise and hacking skills. It's the danger zone. It's the kind of data science team that can produce interesting numbers, and since they have the expertise, they can also produce numbers that are relevant to the business user. But these insights are often misleading, and they pretend a precision that is just not true. So I guess the morale of this is respect your statistician. He should be able to foresee and circumvent most of the difficulties that I've presented before. All right, so I hope you found something to take with you from this presentation. Here are the 3 points that I wanted to bring across. So the first thing to notice is the availability of sensor data that is currently increasing with more and more devices or things being connected to the Internet. And this offers a whole new world of possibilities for data science and predictive analytics that goes beyond the well-known cases of, let's say, I don't know, customer targeting or the forecasts of financial metrics. Secondly, in order to provide insights rather than mere predictions, you can use a method called regression analysis that I introduced to you, and that can quantify how certain predictors influence a target value. And lastly, working with sensor data comes with some very specific challenges. It is unreliable, it's messy, it also has a lower information density, meaning that the insights that you can sort of extract per megabyte of data is a little bit lower than, let's say, with transactional data. But these difficulties can be overcome when they're rightly addressed. That's basically it. Thank you very much for listening. What I wanted to mention towards the end, SAP also provides tools that can help you to overcome the problems that I explained to you, and that can help you with creating regression analysis problems. It's called SAP Predictive Analytics. So we have actually two sets of tools. One tool is more automatic, that is more tailored to people who are not so much familiar with data science, but we also have expert tools that are for the data scientist.